Okay, following up on integration, we come to integration of special type of functions. In this case, we're going to attack natural logs. Notice that if we have the integral of 1 over x, we have an issue if we try to do our reverse power rule. I mean, that'd be x to the negative 1, so if we bump that up, we'd get x to the 0. We'd try to multiply through by a reciprocal, and we'd be a little lost. So what we understand is the integral of 1 over x is natural log of x, denoted ln x. So let's talk about properties of ln x for a moment. If y is equal to ln x, then its graph looks something like this. Its domain is simply every positive x value. Its y's can be negative and positive. It is continuous and smooth. It is increasing, and it is always concave downward. All right. One property about it, or I guess another couple properties about it, is the point 1, 0 exists on the graph. If I take the natural log of 1, I get 0. And also, if you're talking about area underneath the curve, eventually we'll hit this special function, this special number e here, and I'm sorry that looks like an L, it's an e, which is approximately 2.718. And e is a number such that the integral underneath, the area underneath, which is the integral, the area underneath the natural log curve between 1 and e is 1. So basic concept would be the integral with a lower bound of 1 and an upper bound of e of the natural log function would give us 1. All right. So let's talk about it in reverse then. If y is equal to ln x, then y prime is 1 over x. Obviously, an antiderivative and a derivative should cancel each other out. And in general, if I take the natural log of a function and I want its derivative, I just take that function in the denominator and its prime in the numerator. All right, so it's u prime over u. So an example would look something like this. If I had the original function was the natural log of x squared plus 2, then the derivative is 2x over x squared plus 2, which again is the original in the denominator and the derivative in the numerator. If I look at some properties of natural log of 1 is 0. If I have natural log of a product, I actually add those things, natural log a plus natural log b. If I have natural log of a to the nth power, I bring an exponent out front and I leave natural log of a inside. And of course, if I have a quotient, it's ln a minus ln b. We might have expected that, being that these two rules look a lot like when I multiply like bases, I add or subtract exponents based on multiplying or dividing like bases. Okay. A couple examples would look like this. If I have the natural log of rad x squared plus 1 and I want its derivative, I first rewrite. I use that rule that says natural log of x squared plus 1 to the 1/2 power is actually bring the exponent out front, 1/2 ln x squared plus 1. And then I just take the derivative, which is the original in the bottom, and the derivative of that little part in the top. The 2's cancel, and I'm left with x over x squared plus 1. If I looked at a little trig, natural log of x sine x, I separate these using that product rule. So instead of x sine x, I get ln x plus ln sine x. And then again, I use the rule about its derivative over its original, 1 over x in this case. The derivative of sine x is cosine x, so cosine x over sine x in this case, which is 1 over x plus cotangent of x. We'll probably split this homework into 2 parts. The first part will be looking at some graphs and manipulating those rules, those power rules and those exponent rules and those things like that. We're going to manipulate some natural log functions. And then in part 2, which we'll probably get to a day later, would be when we start doing the derivatives part of it. So we'll start doing the derivatives and that in the next day. So here's the rest of that. And we'll go quite a ways. And this will all be in something called Chapter 5 folder in your shared resources. Thanks.